All right, so let's get started talking about our problems for AC circuits. So to start with, we just had a few poll questions, just kind of reviewing some basic stuff about capacitors and inductors, specifically related to, we put them in a circuit with a resistor and a power supply. What are their short and long-term behaviors? So for example, like with the capacitor, if I hook it up to a power supply, it takes some time to charge, meaning that at time 0, right, then I end up with no potential and a large amount of current as the capacitor charges. And as time heads toward infinity, the capacitor voltage increases and I have no current once the capacitor is full. So with the inductor, then the voltage depends on the change in current. So when I first throw the switch, I have a large voltage and no current. I can think about the inductor as providing a kind of inertia for the current in the circuit. And as time goes by, the current reaches a steady state, and so I have no potential in the inductor. So the oscillatory circuits are going to be composed of an inductor and a capacitor in series with one another. So there's a few different ways we can understand the circuit, but we're just basically going to use the same circuit rules we used last quarter. So the main one is keeping track of the loop. So if I draw a loop around the circuit, it's going to include the capacitor and the inductor. And so I can set the voltage of the capacitor equal to the voltage of the inductor because my total change in voltage should be 0 as I make a loop around. So I can use that to set the charge equal to the voltage, or charge over the capacitance equal to the inductance times the negative change in current over time. And I know that the current is the change in charge over time. So if I plug that in, I'm going to end up with a differential equation for charge. And it's a differential equation that we've seen a few times. And this is why we do this unit after talking about simple harmonic oscillators, because the differential equation that describes this system is the same differential equation that we saw with the simple harmonic oscillator. The difference is now what's oscillating is the current. But if the current's oscillating and the current looks like a sine or a cosine function, well, the voltage is the derivative of current, so that's going to look like a sine or a cosine function. And then the charge is the integral of the current, so that's going to look like a sine or a cosine function. So we can think about the charge, voltage, and the current as all being things that are isolating or oscillating. So if I make the simple harmonic oscillator equation look a little bit more familiar, right, I can remember that this stuff out in front of the function was what we said was omega squared. So omega is going to be 1 over LC, and I can use that to find the frequency and period of this oscillatory circuit. So if I want to sketch kind of what this oscillation actually looks like, it looks a little bit different than something like a pendulum, even though it obeys all the same equations. So instead of trading energy back and forth between like kinetic and potential energy, we're trading energy back and forth from the capacitor to the inductor. So when the capacitor has all the energy, the capacitor is fully charged, which means there's no current. And then as the capacitor starts to discharge, the current starts to flow. At the moment where my current is maximum, that means all of my energy is in the inductor, none is left in the capacitor, and so my capacitor must be empty. That's going to be what we could consider to be a quarter of the period. If I keep going around the oscillation at a half period, now the current's been flowing and the capacitor is charged up in the opposite direction. It'll start to discharge and then the current will flow in the opposite direction and we'll complete a loop, or an oscillation in this way with energy traded back and forth between the inductor and a capacitor. So, right, conservation of energy was really useful when we talk about oscillators, so it's worth checking in that we remember the energy stored in a capacitor and the energy stored in an inductor. For a capacitor, right, I want to add up all the charges times the voltage, right? Voltage times charge gave me potential energy. So I really want to integrate over all of the charges and multiply times the voltage, right? The voltage is not going to be constant as I charge this capacitor up. when I start putting charges on the plates, right, each charge I put on increases the voltage. And so I end up wanting to write this as an integral from empty to full. And then I arrive at Q squared over 2 times the capacitance. And I can substitute Q is equal to capacitance times voltage to get the potential energy equation for a capacitor that we might be more familiar with. For the inductor, I've got the stored energy increases with increasing current. We may not have actually had a chance to get to this equation last quarter, but the energy stored in the inductor is given by the inductance times the current squared over 2. So if I throw a resistor in this circuit, so now I have an inductor, capacitor, and a resistor, the analogy we want to draw is like adding friction into our oscillator system. So when we added friction to a pendulum or to the mass in the spring, we had the total energy was decreasing over time. In this case, the same sort of thing is going to happen. The total amount of energy in the circuit is going to decrease over time. The resistor is going to convert electrical energy into thermal energy. And so we're going to have less and less energy as the oscillator goes back and forth. So that means, qualitatively means the same thing that it did for simple harmonic oscillators, in that the frequency and the period, which don't depend on the amplitude and don't depend on the energy, remain constant. And the amplitude of the current and the amplitude of the voltage functions, which do depend on the energy, those will decrease over time. So this is a really close analogy to like the hula hoop with friction. Half of our topic is connected to AC circuits, and this is where things start to get a little bit different. So I'm replacing the battery, right, a constant voltage power source, with some sort of power source that's providing an oscillating current or an oscillating voltage, right? Typically, we set the voltage of the battery, and whatever current comes out depends on what circuit I hook it up to. For an AC circuit, we might be at the voltage, or we can express it as a voltage and have to figure out the current. So when we talk about AC circuits, the kind of stuff we're going to be interested in is figuring out the current and voltage functions with respect to time, the average and the peak power. We want to think about how adding capacitors, inductors, and resistors affects the circuit. So this is going to be in the form of impedance. We want to be able to write out the voltage and current in every item in our circuit. So the difference between this and DC circuits is this is always going to be a function of time. And we want to compare how the voltage and the current might change in RLC circuits as I add different elements to the circuits. And that's where we get things like power factor and phase shift, resistance, reactance, and impedance. So if I want to start off with the easiest case is probably just having a resistor, because the voltage and the current, if I compare them in the resistor, they're going to obey the same function of time. The resistance is just going to give me a constant proportionality between the voltage and the current, constant value. So if my current is a sine function, then my voltage is a sine function. If I want to find the power, right, I can't just take a simple average, which will always give me 0. That won't really reflect the situation. So we develop the RMS, right, where we square the function, then we take the average, then we take the square root. If we have a perfect clean cosine function or sine function, this works out really nicely. It just gives us the amplitude divided by root 2. So that's a fairly simple way to switch back and forth. So let's see. I think we don't need to talk too much about this since everybody did fine with this one. So where things get more complicated and tougher to figure out is related to what's going on with the voltage versus the current when I start adding things like capacitors and inductors into the circuit. So capacitors and inductors now, in addition to changing the effective maximum current, I also start adding phase shifts. So now the current is no longer going to be largest when the voltage is largest. So for the capacitor in particular, when the voltage is largest, I know the current is 0. So the voltage being largest is when the capacitor is fully charged, if you remember. So I can come up with an equation for current as a function of time by taking the capacitance times the derivative in voltage with respect to time. So that gives me a function for current. And I can rearrange that to get a nice relationship between the maximum current and the maximum voltage in a capacitor, or the amplitude of the voltage as a function of time versus the amplitude of the current as a function of time. And so this X sub C, right, what we call the capacitive reactance, 1 over omega C, that is going to end up having the same units as resistance. It's going to be in ohms, effectively. So the ratio between voltage and current isn't given by resistance anymore. In this case, it's given by reactance. But there's more than just that happening, because we also have this phase shift. So in a capacitor, we say that the current leads the voltage. So we say that because if I graph current and voltage next to each other versus time, I'm going to see that I reach peak current before I reach peak voltage. So we say that the current is in the lead. So the way we can express this is by adding a pi over 2 phase shift to the current relative to the voltage, or subtracting a pi over 2 phase shift from the voltage relative to the current. If I look at an inductor, the voltage is a constant times the derivative of the current with respect to time. So something similar is going to happen, but I'm going to be shifting the curve the other way. So now in a circuit with an inductor, now the voltage is leading the current, or the current is lagging behind the voltage. The ratio of the maximum values is now given by the inductive reactance, which is L times omega. So these phase shifts show up in capacitive and inductive elements, in addition to scaling the maximum current relative to the maximum voltage. What we also realize about these reactances is that they don't just depend on the capacitor and the inductor, they also depend on omega. So they depend on how fast I'm trying to wiggle the circuit back and forth. If I'm oscillating very quickly, then the inductor is actually going to resist more, right? The inductor resists rapid changes in current. So even if I have the same inductor, if I'm trying to increase the frequency, I'm going to have more reactance out of the inductor. So it depends not just on the circuit elements, but also on the frequency. So as a result, that means if I take a circuit with an AC power source and I start adding things, I start adding resistors, capacitors, or inductors in some combination, what's going to change? It could change the amplitude, right? In the same way that adding a resistor could change the amplitude, and it can change the phase. So I could be changing when the peak of the current function happens relative to the peak of the voltage function. I would not change its frequency. So if I am driving the circuit with a power source that's oscillating 60 times per second, then the charge on the capacitor is going to be oscillating back and forth at the same frequency, 60 times per second. My resistors, capacitors, and inductors won't be changing the frequency of the circuit. So there's a lot of different conventions.
I have a question about that real quick.
Yeah. Go ahead.
So there was an equation in the book, I believe it said like omega is the square root of 1 over LC. Doesn't that show a relationship between the frequency and the inductance and or capacitance?
So you want to be careful, because that was an equation from the oscillating circuits. So those were circuits that we had no driving power source. So if I have an inductor and a capacitor but no power source, they'll have a natural frequency of oscillation that depends on L and C. But if I have a power source in these AC circuits that's driving with a certain omega, we'll always be oscillating at that omega that I'm driving it at.
Gotcha.
Good question. Okay, so the kind of concise way to put all this stuff together with R's and L's and C's and to kind of work out the conventions with the phase is to take the current, right? So I typically will specify the current, because if we're dealing with a series circuit, which we typically are just because they're a little bit more straightforward to work with. If we're driving with a certain frequency, then I'll start with that and I'll call that a sine or a cosine function. I'll define the phase as something I add to the argument inside the sine function to find the voltage. So I'll be defining phase in terms of whether the voltage is ahead or behind of the current, typically. You could do either way. I've seen other books do either way. This is the way that I'll just refer to it. And in terms of the overall ratio between the amplitude of the voltage and the current, we can combine all the different effects of the R, C, and L to get the impedance, which we just label as Z, and it's going to have units of ohms. So in this kind of concise equation, the impedance is this kind of square root of the reactances, or I take the inductive reactance, subtract the capacitive reactance, square that whole thing, add the resistance squared. That gives me the impedance. And if I want to find the phase offset that the voltage has relative to the current, I basically take an inverse tangent function of the difference between the reactances over the resistance. So this kind of looks like Pythagorean theorem and like finding an angle. And there are lots of ways to interpret it that way. Specifically, if you take something like complex analysis or an electrical engineering course, you'll probably learn to interpret it that way. But for in here, we can just think about it with these equations. We don't have to try to draw any kind of strange geometry out of it. So yeah, so going back to that case where omega was 1 over LC, that was the frequency of an inductor and a capacitor together. So that frequency is not the frequency of oscillation for an AC circuit, but it's still very interesting because if I do try to drive the circuit at that frequency, that's the frequency where the inductive reactance is equal to the capacitive reactance. So if I drive it at that frequency, we hit what we call a resonance condition. And so that's going to be the frequency that gives me the minimum impedance or the maximum current. So that's the frequency where the inductor and the capacitor effectively cancel each other out because they're not really resisting what's going on. They're happy to be oscillating at that frequency, which is the frequency they would oscillate if they weren't being driven. So that's kind of fun and interesting. But in no way do I have to drive an AC circuit at that resonance frequency. I can drive it at any frequency and the voltage and current will be functions of that frequency. So with this definition of phase, this is what my leading and lagging phases look like. So when I talk about like a lagging phase, it's like a circuit that has inductors in it. So that would be a phase greater than 0. If I have a phase that's less than 0, then that's the voltage leading the current. So that would be something like a circuit that has mostly capacitors in it. So if I now go to calculate the RMS power, I'm in a slightly different position because my current and voltage are no longer happening or no longer peaking at the same time. So basically, the larger this phase angle, the smaller the effective power I'm going to have is. So we use this cosine of phi, we call the power factor. If my phase is 0, then my current and voltage are peaking at the same time. And so I'm getting the largest amount of power for a given current and voltage. If that phase gets big, then I'm producing less power because power, product of voltage and current, if they're not peaking at the same time, then I'm going to not have as much power. Okay, so that brings us to kind of our last check-in problem that we worked on, If I have a known voltage and a known current source connected to a resistor, an inductor, and a capacitor, in series. Ooh, wait, hang on. Sorry, getting ahead of myself. This is not that last problem. So this is the previous one. So if I know the voltage and the current, right, and I know the power factor, then if I want to find the power, right, I just need to look at the voltage, the RMS voltage, the RMS current, and this phase difference. And so when I say that the current is leading the voltage by a certain phase, so 26.5 degrees, then that would be the phase that I would add to the voltage. So the way I've done my sign convention, if I wrote the phase inside the voltage function, that phase would be negative. Or in other words, if the argument of the sign function for current, if I put a 0 in there, I'd get 0 current. But if I plug 0 in for time in the voltage, right, I should get a negative current or negative voltage, because the voltage function should be ahead of the current. So in this case, right, I would write sine omega t minus, and it would be plus 26.5 degrees. Okay, so if I put those values in, I get an average power of 1,687 watts. Okay, this is the last problem that I thought we were on before. So the last problem we did, we had a driving current, right, where the source is producing 14.5 amps times cosine omega t. So yeah, this 45 inverse seconds, that's our omega. And I connect it to an RLC circuit in series, and I know the resistance, capacitance, and inductance of all three elements. So if I want to write out voltage, right, the voltage, the thing I need to figure out is what's the maximum voltage, or what's the amplitude, and what's the phase. Finding the amplitude of the voltage in terms of the amplitude of the current boils down to finding the impedance. So there's really two things I need to calculate here. I need to find the impedance, and I need to find the phase. So for the impedance, right, I can calculate it from omega, L, C, and R, and I get 60.6025 ohms. For the phase, right, I can calculate it in terms of L, C, and R, and omega using this inverse tangent function, and I get something like 0.09 radians. So plugging into my voltage function, this would be 0.09 radians, right? And I could take the impedance times the current, so it would be I max times 60.25 ohms. And yeah, it's a little bit trippy for, right, omega times an inductance to give me ohms. But yeah, it does work out that way, which is cool. So when I want to find the voltage function for each element in particular, for the resistor, that's straightforward because I just take the current function as a function of time and multiply it times the resistance. For the inductor and capacitor, right, then I am going to be shifted one way or the other. So for the capacitor, I can multiply by the capacitive reactance rather than by the resistance, and I get phase shifted from a cosine function to a sine function. For the inductor, right, I can multiply by the inductive reactance, so omega times L rather than the resistance, and I get shifted to a negative sine function. So one thing I did see when I was looking through the responses on the board is most people give the same phase shift to the capacitor and the inductor, but we need to be careful that those voltages are getting shifted in different directions. So one's getting shifted to become a positive sine function, that's going to be the capacitor, and one's being shifted to a negative sine function. And so we can kind of keep track of equations for that, or we can go back to, right, that the voltage from a capacitor is like the charge times or charge over the capacitance, and I can relate the charge to the current, right? The current is going to be the derivative of charge over time. So I could use the differential equations we were using back at the beginning, or I can just keep track of which direction that phase shift should be for each element. All right, and with that, I don't believe I have anything else I need to talk about. So I'll stick around for a little bit if anyone has questions. This will be posted, recorded as usual. If you don't have questions,